Voyager 1, a tiny spacecraft the size of a car, is drifting through the unimaginable darkness of space, 14.5 billion miles from Earth. But nearly 50 years later, Voyager is still alive, defying the odds. Recently, this legendary probe has encountered something in the void that has scientists both amazed and deeply concerned. What has there found Voyager? The data streaming back suggests phenomena that challenge everything we thought we knew about interstellar space. Today, we explore Voyager's impossible encounter and what it means for humanity's future among the stars. The birth of a star sailor. The story of Voyager 1 began in the era of Cold War ambition, when NASA sought to expand humanity's horizons beyond Earth orbit. Under the leadership of Dr. Edward Stone, Voyager 1 was designed as a robust spacecraft capable of a grand tour of the outer planets, the first of its kind. Launched on September 5, 1977, from Cape Canaveral, it journeyed towards Jupiter with an array of scientific instruments, including the cosmic ray detector and plasma wave instrument. The spacecraft was engineered to survive decades of space exposure, carrying the hopes of mankind as it ventured boldly where no one had gone before. Dr. Stone's decade-long stewardship ensured the mission's remarkable longevity, setting the stage for an unprecedented exploration of our solar system. Built with 1970s technology that would seem primitive by today's standards, Voyager 1 was nevertheless equipped with instruments sensitive enough to detect the faintest signals from the cosmos. The spacecraft's nuclear power source, designed to last far beyond its primary mission, would prove crucial for its extended journey into the unknown. This remarkable engineering feat would soon carry humanity's message to the stars and beyond. The Grand Tour. Voyager 1's Grand Tour of the solar system became legendary, lasting over 12 years and bringing humanity close to the gas giants Jupiter, Saturn, Uranus, and Neptune. During flybys, it sent back unparalleled images and life-changing data that redefined our understanding of these colossal planets. Notably, the encounter with Jupiter revealed the planet's turbulent atmosphere and intense magnetic field, reshaping planetary science forever. The spacecraft discovered active volcanoes on Jupiter's moon Io and revealed the complex structure of Saturn's rings in unprecedented detail. Subsequent visits to the outer planets expanded our knowledge of ice giants and their mysterious moon systems. Each planetary encounter used gravitational assist to propel Voyager faster toward the edge of the solar system, a trajectory carefully calculated to maximize scientific return. The spacecraft's cameras captured images that became iconic symbols of human exploration, including the famous pale blue dot photograph of Earth taken from 4 billion miles away. Voyager's trajectory, programmed for a final sprint beyond the solar system, demonstrated NASA's engineering brilliance in interplanetary travel. Today, its legacy continues as it ventures into interstellar space, humanity's first emissary beyond the protective bubble of our sun's influence. The Golden Record. The Golden Record aboard Voyager 1 is a time capsule destined to outlast humanity itself, containing sounds and images representing Earth's diversity. Curated by Dr. Carl Sagan and a committee of scientists and artists, the record includes greetings in 55 languages and music spanning cultures and epochs. Encased in an engraved gold-plated copper disc, it serves as a cosmic message in a bottle, intended for any intelligent life that may encounter it in the distant future. The record also contains scientific information about Earth's location, using pulsar maps devised by Dr. Frank Drake, providing a cosmic roadmap for potential discoverers. Despite its age, the Golden Record remains a testament to human curiosity and hope across the void of space, symbolizing peace and universality. The record includes sounds of Earth, from ocean waves to human heartbeats, from classical music to the laughter of children. It represents humanity at its best, showcasing our diversity while emphasizing our common bonds. Voyager's legacy is as much cultural as scientific, immortalizing humanity beyond our solar system boundaries. This golden message continues its journey through the cosmos, carrying our hopes and dreams to destinations unknown. Years in the void. Years of drifting through the cold void beyond our solar system, Voyager 1 has defied all expectations for spacecraft longevity. Since crossing the heliopause in 2012, it has continuously sent back data about interstellar space despite operating far beyond its design limits. Engineers at NASA Jet Propulsion Laboratory, led by Dr. Suzanne Dodd, have managed to keep the spacecraft operational despite dwindling power supplies and aging components. Voyager's instruments continue to measure the harsh radiation environment far beyond any planet's protective magnetosphere, revealing a cosmos more dangerous and dynamic than anyone imagined. The spacecraft's telemetry reveals vital signs including temperature readings and electrical system status, a testament to the incredible engineering resilience of 1970s technology still performing flawlessly in the most hostile environment known. Each year, Voyager's plutonium power source weakens, forcing mission controllers to make difficult decisions about which instruments to shut down to conserve energy. Yet the spacecraft persists, transmitting scientific data across billions of miles of empty space. Voyager 1's longevity contrasts sharply with initial mission expectations, with scientists noting it has become humanity's longest-lived emissary in the cosmos, far exceeding all predicted operational timelines. Crossing the boundary. Voyager 1's historic crossing of the heliopause marked humanity's first journey into true interstellar space, a milestone that redefined our understanding of the cosmic frontier. The spacecraft's instruments, including sophisticated sensors and detection equipment, began recording phenomena unlike anything seen within our solar system's protective bubble. Lead scientist Dr. George Glockler from the University of Minnesota explains the significance of these observations, revealing magnetic field turbulence and unexpected plasma oscillations that challenge existing models of the interstellar medium. The boundary between solar and galactic space proved far more complex and dynamic than theoretical predictions suggested, showing multiple layers and transitional zones rather than a clean separation. Voyager's data revealed that interstellar space is not the quiet, empty void scientists once imagined, but rather a region filled with electromagnetic activity and cosmic phenomena. The spacecraft detected charged particles moving at incredible velocities, evidence of ancient stellar explosions and cosmic events that occurred millions of years ago. These measurements provided the first direct sampling of materials from beyond our solar system, offering insights into the composition and behavior of the galaxy itself. Voyager's continuing transmission from this unexplored realm offers unprecedented insights into the boundary between solar influence and the vast galactic ocean beyond our protective heliosphere. Signals from nowhere. In late 2023, Voyager 1 went mysteriously silent, sparking fears among mission scientists who had dedicated decades to the project. Analysis revealed a corrupted memory chip, likely damaged by a high-energy cosmic ray that struck the spacecraft with devastating precision. Immediate action by the Jet Propulsion Laboratory team, including Flight Director Dr. Melissa Brown, involved rerouting computer operations to back up memory areas while working across an impossible distance. This delicate software workaround, performed from Earth with signals taking over 22 hours each way, required extraordinary precision and patience from the engineering team. The rescue operation demonstrated incredible human ingenuity, essentially performing remote brain surgery on a patient billions of miles away using technology older than most of the engineers working on it. When Voyager finally responded, it brought relief to scientists worldwide who had feared losing humanity's most distant explorer forever. The incident highlighted both the spacecraft's vulnerability and resilience, showing how a single cosmic particle could threaten decades of scientific discovery. The successful restoration of communication proved that even in the depths of interstellar space, human determination and technical expertise could overcome seemingly impossible odds and continue our journey of cosmic exploration. The temperature mystery. Voyager's instruments have detected bizarre temperature anomalies in the interstellar medium that defy current scientific understanding of cosmic thermodynamics. The spacecraft's sensors recorded unexpected heat signatures and thermal variations that suggest unknown energy sources operating in supposedly empty space. Dr. Reka Winslow from the University of Michigan analyzed data showing these temperature fluctuations correlate with mysterious electromagnetic activity that creates complex thermal gradients across vast distances. These findings indicate dynamic processes previously unknown to science, with energy transfers occurring through mechanisms that current physics cannot fully explain. The spacecraft's thermal sensors detected variations that challenge existing models of interstellar space, revealing an environment far more active and energetically complex than anticipated. These thermal anomalies persist across the spacecraft's trajectory, creating a puzzle that has scientists scrambling to develop new theories about energy distribution in interstellar space. The temperature readings suggest that the void between stars, may harbor energy sources or phenomena that could revolutionize our understanding of cosmic physics. Some researchers speculate these thermal signatures could indicate the presence of dark matter interactions or unknown electromagnetic processes that operate on galactic scales, opening entirely new avenues for astrophysical research and discovery. Changing course. Maintaining control over a spacecraft traveling through the depths of interstellar space requires unprecedented precision in navigation techniques and trajectory management. Dr. Carlos Hernandez from NASA Goddard Space Flight Center leads efforts to execute delicate course corrections on Voyager 1, despite the enormous challenges posed by distance and communication delays. These trajectory adjustments must account for the spacecraft's changing orientation, limited fuel reserves, and the gradual degradation of its attitude control systems after decades of operation. The complex calculations required for each maneuver consider gravitational influences from distant stars, the pressure of interstellar particles, and the spacecraft's slowly declining power output. These adjustments demonstrate unparalleled precision in space navigation, requiring engineers to predict and compensate for factors that won't be observable for hours due to signal travel time. Each course correction represents a carefully calculated gamble, as there are no second chances when working with such precious and irreplaceable scientific assets. The navigation team must balance scientific objectives with spacecraft preservation, making difficult decisions about energy expenditure and pointing accuracy. Despite these challenges, Voyager continues to maintain its scientific mission while heading toward an eventual encounter with the star AC plus 79 3888 in approximately 40,000 years. Ghost in the machine. Recent months have seen Voyager 1's onboard computer systems exhibit mysterious glitches that have puzzled mission engineers and raised concerns about artificial intelligence anomalies. Led by Dr. Ananya Singh at NASA's Jet Propulsion Laboratory, the team closely monitors these strange behaviors manifesting as unexplained error codes and signal irregularities that don't match any known failure modes. The anomalies appear almost intelligent in nature, as if something within the spacecraft's systems is learning and adapting to its environment in ways the original programmers never intended. Some engineers speculate these phenomena arise from cosmic radiation effects interacting with the spacecraft's aging electronics in unexpected ways, while others wonder if decades of exposure to interstellar conditions have somehow altered the computer's fundamental operations. The spacecraft occasionally transmits data patterns that seem to contain information beyond its programmed capabilities, leading to speculation about whether the harsh environment of space might be inducing evolutionary changes in electronic systems. Diligent troubleshooting and software updates aim to preserve communication integrity, but the mysterious behaviors continue to manifest despite all efforts to understand or control them. These electronic anomalies represent one of the most puzzling aspects of Voyager's extended mission. Patterns within patterns. Recent analysis of Voyager's long-term data has revealed subtle but persistent patterns in cosmic ray measurements and magnetic field variations that suggest influences from unknown astrophysical sources. Dr. Emilia Garza, a heliophysics expert from the University of Texas, notes the discovery of quasi-periodic oscillations that appear to originate from deep space phenomena beyond our current understanding. These patterns within patterns challenge assumptions about the uniformity of interstellar space, instead revealing a complex structure operating on multiple scales and timescales that scientists are only beginning to comprehend. The oscillations show characteristics that don't match any known natural phenomena, leading some researchers to speculate about possible artificial origins or previously unknown physical processes occurring in the galactic environment. Voyager's instruments detect synchronizations and correlations in the data that seem too organized to be purely random, suggesting underlying mechanisms that organize matter and energy across vast cosmic distances. These discoveries have profound implications for our understanding of how the galaxy operates, potentially revealing hidden structures or forces that influence the behavior of matter and energy throughout interstellar space. The patterns continue to evolve as Voyager travels deeper into unexplored regions, providing humanity with its first glimpse into the true architecture of our galactic neighborhood and the mysterious forces that shape it. Voyager 1 continues its impossible journey into the cosmic unknown, revealing mysteries that challenge our understanding of the universe itself. From strange temperature anomalies to unexplained computer behaviors, this tiny spacecraft has encountered phenomena that suggest the cosmos holds secrets far beyond our current knowledge. As it drifts ever deeper into interstellar space, Voyager carries not just our scientific instruments, but our hopes and fears about what lies beyond our protective solar bubble. Subscribe to Stellar Tech for more revelations about humanity's greatest adventure and the discoveries that await us in the darkness between the stars. What if the first definitive proof of alien technology wasn't a grand arrival, but, just a single ambiguous frame of data on a NASA live feed, visible for only a fraction of a second before the screen went black? This is the story of a hypothetical event, a thought experiment grounded in real science. On June 18th, a NASA feed tracking a fictional interstellar visitor named 3I Atlas suddenly cuts out, but not before revealing something that looks eerily artificial. Was it a simple glitch or maybe our first glimpse of something engineered? Let's explore this together. The initial discovery. So, how does a story like this even begin? Well, it starts with the silent, relentless work of a real program, the Asteroid Terrestrial Impact Last Alert System, or ATLAS. Funded by NASA and operated by the University of Hawaii, this network of robotic telescopes with key figures like principal investigator Larry Deneau at the helm, scans the entire visible sky every 24 hours. Its primary mission is planetary defense, but its wide, fast survey is perfect for catching interstellar interlopers. In our scenario, on July 1, 2025, ATLAS flags an object on a hyperbolic trajectory. This isn't just another rock orbiting our sun. Its path proves it's a visitor from another star system, moving way too fast to be captured by our sun's gravity. After its trajectory is confirmed by the Minor Planet Center, it's designated 3Y Atlas. This would immediately trigger a global astronomical response. Scientists like Karen Meach, who led the characterization team for Oumuamua, would spearhead campaigns to observe the object with every major telescope available. This isn't just about getting a picture, it's a frantic race against time to gather data on a messenger from a distant, unknown solar system before it disappears back into the void forever. The anomalous frame. Here's the moment a routine observation becomes honestly a profound mystery. A public live feed is tracking 3I Atlas. At precisely 0317 and 12 seconds UTC, the feed freezes on a final frame before cutting to black. The image is mostly standard deep space fare, a dim, fuzzy nucleus surrounded by a cloud of gas and dust. But in the lower left quadrant, something is different. There is a razor-sharp glint of reflected sunlight forming a perfectly straight line. This is the kind of anomaly that would make a SETI pioneer like Jill Tarter take notice. Natural objects in space, comets, asteroids, dust clouds, are chaotic and irregular. Light scatters off them in diffuse, uneven patterns. But this glint is geometric. It behaves as if it's reflecting off a polished, flat surface. Independent astronomers running their own analysis software would see their edge detection algorithms flag the segment immediately. It's too consistent, too crisp. In the long search for extraterrestrial intelligence, this is exactly the type of techno-signature researchers look for, an artifact that appears manufactured, standing out starkly against the random backdrop of nature. The question is no longer just what is this comet made of, but was a part of it made at all? Data verification. An image this provocative is, well, worthless if it can't be authenticated. This is where the modern, decentralized nature of science communication becomes critical. In the minutes after the blackout, a global network of independent archivists and citizen scientists would swing into action. They run automated scripts that continuously record public NASA feeds. Packet captures of the 3I Atlas feed from servers in Germany, Australia, and the United States would be uploaded to multiple repositories. Each file, time-stamped 0317 and 12 seconds UTC, is protected by a unique cryptographic hash, a long string of characters serving as a digital fingerprint. This concept, with roots in the work of cryptographers like David Chaum, ensures data integrity. When compared, every single archived file matches, bit for bit. The German hash is identical to the Australian hash, which is identical to the original broadcast. This provides undeniable proof that the frame was not altered, manipulated, or a hoax created after the fact. The chain of custody is forensically sound, the evidence is clean. The anomaly, whatever its cause, was genuinely present in the data stream from the spacecraft. This eliminates any possibility of a simple prank and honestly forces the scientific community to confront the data as it is. Technical explanations. Before we entertain alien explanations, we have to exhaust all the mundane ones. So, why did the feed drop? The most probable official reason would be a routine network handover. NASA's deep space communications are a marvel of engineering, managed by experts like those at the Jet Propulsion Laboratory, but they aren't flawless. Signals travel from a spacecraft to a relay satellite in the Tracking and Data Relay Satellite System, or TDRS, then down to one of the 3 deep space network complexes on Earth. As the Earth rotates and satellites move, the signal must be handed off from one station or satellite to another. An engineer like Mark Raymond, known for his work on missions like Dawn, would explain that these handovers can occasionally cause a brief loss of signal. These handover blanks are common, logged, and typically last for a few seconds. They show up as a gap in the data logs with a specific reason code, so a blackout is not in itself a conspiracy. The entire system is built with these brief interruptions in mind. The deeply unsettling part of this scenario isn't the blackout itself, but its timing. A routine technical glitch occurring at the exact nanosecond a potentially paradigm-shifting anomaly appears on screen is a coincidence of astronomical proportions. Digital forensics. Let's put the frame itself under the microscope. Digital forensics is an unemotional discipline, and it offers 2 powerful non-exotic explanations for the straight edge. The first is video compression. To transmit massive amounts of data across millions of miles, images are compressed using algorithms like JPEG or MPEG. These codecs, whose development owes thanks to computer scientists like Ken Perlin for their work on procedural textures and noise, divide an image into an 8x8 pixel grid. When a faint linear feature happens to align with the grid's boundaries, the algorithm can snap it into a perfectly straight line, exaggerating its geometric appearance. It's an artifact of the math, not a feature of the object. The second culprit is a cosmic ray. Space is saturated with high-energy particles that constantly bombard camera sensors. A particle can streak across a sensor's pixels, leaving a bright, and often perfectly straight trail that lasts for only a single frame. This is a well-documented phenomenon. The most likely forensic conclusion would be a double hit. A cosmic ray created a faint streak that was then amplified and sharpened by the compression codec. It's an elegant, logical explanation that fits the evidence without rewriting any textbooks. But it can't entirely rule out that it was a real object that was simply processed by the same algorithms. 3i Atlas background. To grasp the full weight of this anomaly, we need to remember the real interstellar objects that preceded our fictional one. First came one Oumuamua in 2017. It was a complete enigma. Small, dark, and highly elongated, it showed no visible coma or outgassing, yet it accelerated away from the sun as if something were pushing it. This led Harvard astronomer Avi Loeb to famously propose it could be an artifact of extraterrestrial technology, like a solar sail. Then, in 2019 came 2I Borisov. It was a much more familiar sight, looking and behaving like a classic comet with a clear coma and tail, though its chemical composition was unlike anything from our solar system. These 2 real visitors set the stage perfectly. They proved that interstellar objects are a reality, and that they can be profoundly weird. Oumuamua, in particular, primed the scientific community to be on the lookout for anomalies. It opened the door to seriously considering technological origins. So, when 3I Atlas appears in our scenario with its own bizarre feature, it doesn't happen in a vacuum. It lands directly on the fertile ground of unresolved scientific debate and public fascination that Oumuamua left in its wake, making the stakes infinitely higher. Scientific scrutiny. In science, an extraordinary claim requires extraordinary evidence, a principle famously championed by the great astronomer Carl Sagan. A single ambiguous frame from one instrument is the very definition of not enough evidence. For the artificial edge hypothesis to be taken seriously, it would have to survive a brutal gauntlet of scientific scrutiny. First, the observation must be independently replicated. Different teams using different telescopes, like the Hubble Space Telescope or the Keck Observatory, would need to observe 3I Atlas and confirm the presence of the same geometric glint. Second, it needs to be a multi-wavelength detection. If the glint appears in visible light, does it also appear in infrared and ultraviolet? spectral analysis of the glint itself would be crucial. If the light signature matched a known metallic alloy rather than silicate rock or water ice, the claim would gain significant credibility. As it stands in our scenario, the evidence is anecdotal. It sits on the lowest rung of the evidence ladder. Until multiple independent data streams confirm the same anomaly, the overwhelming majority of scientists would rightly remain deeply skeptical and favor a natural or instrumental explanation. The burden of proof is and must be incredibly high. 3 theories. After all the analysis, the scientific community and the public would be left grappling with 3 divergent paths. The first is the most conservative natural phenomena. A leading cometary expert, perhaps someone like Paul W. Chodas from NASA's Center for Near-Earth Object Studies, would argue that what we saw was a glint off a freshly exposed face of ice. Comets are dynamic bodies. As they heat up, jets of gas can erupt, putting immense stress on the nucleus and causing it to fracture. A large, flat piece of ice could easily shear off, and if it catches the sunlight at just the right angle, it would produce a sharp, geometric glint before tumbling away. The second path is the technical glitch theory, a perfect storm of a cosmic ray hitting the sensor in a straight line, which is then exaggerated by the video compression algorithm. It's an illusion born from the interplay of physics and software. But the third path, the one championed by thinkers like Avi Loeb, is the most profound. It posits that the object is not natural at all, that the edge is a real manufactured component of a larger object, a probe, a solar sail, or even a piece of interstellar debris from a civilization long gone. It is a long shot, but it remains a possibility that cannot be disproven with the available data. Broader implications. An event like this, even a fictional one, would transcend the world of astronomy and have profound societal implications. As Seth Shostak of the SETI Institute has often noted, the discovery of potential intelligence would change our perspective on everything. The immediate aftermath would be a firestorm of public debate about data transparency and potential cover-ups. Why did the feed cut out? Who made that decision? This would lead to intense pressure on government agencies like NASA to adopt even more radical open data policies, perhaps mandating decentralized real-time public archives for all raw telemetry. Funding priorities in science could shift overnight. Congress might allocate emergency funding to projects dedicated to the search for techno-signatures. The event also becomes a massive test of global media literacy. How does the public distinguish between credible scientific analysis and wild speculation? For a world watching, the line between healthy skepticism and unbridled wonder would blur, forcing a global conversation about our place in the cosmos and how we prepare for a discovery that could change humanity forever. One single frame could permanently alter how we look at the night sky. The search continues. While our story of 3I Atlas is a thought experiment, the real search it describes is entering a golden age. We are on the cusp of a revolution in astronomy with the imminent full operation of facilities like the Vera C. Rubin Observatory in Chile. With leading scientists like its director Zeljko Ivazic guiding the project, this observatory will conduct an unprecedented survey of the sky, discovering potentially dozens of new interstellar objects every year. This will transform the field from a data-starved science into a data-rich one. Each new visitor will be a data point, a clue from another solar system. Scientists are now actively developing the AI algorithms and observation strategies needed to characterize these objects quickly and efficiently. They are no longer just looking for comets and asteroids. They are actively hunting for anomalies. They are looking for strange light curves, unusual chemical compositions, and most importantly, objects that move in ways that defy our understanding of physics. The search is on, with more powerful tools and a more open mind than ever before. The next visitor is coming, and this time, we will be ready. The unresolved mystery of the 3I Atlas frame, though fictional, perfectly captures the tension between mundane explanation and profound possibility that drives science forward. It forces us to ask how we would react to a truly ambiguous signal from the cosmos, and highlights the absolute necessity of open data, rigorous skepticism, and relentless curiosity. What do you believe is the most compelling explanation for the anomaly and the blackout? Share your theory in the comments section below. Don't forget to like, subscribe, and hit the bell icon for more deep dives into the greatest mysteries of our universe. Thanks for watching Stellar Tech. September 26, 2022 changed everything we thought we knew about asteroid defense. NASA's DART spacecraft slammed into Dimorphos, a small asteroid moon orbiting the larger Didymos, in humanity's first attempt to deliberately alter a celestial object's path. The mission was supposed to be a simple test: hit the target, measure the orbital change, and prove we could defend Earth from asteroid threats. But what happened next stunned scientists worldwide. The impact didn't just nudge Dimorphos off course, it unleashed something completely unexpected that's still reshaping our understanding of asteroids today. The kamikaze mission DART, Double Asteroid Redirection Test, represented humanity's first planetary defense experiment, designed by NASA's Planetary Defense Coordination Office under the leadership of Lyndon Johnson. The $325 million spacecraft launched on November 24, 2021, beginning a 10-month journey to intercept Dimorphos, a 525-foot-wide moonlet orbiting the larger asteroid Didymos. The mission's objective was elegantly simple yet technically challenging: crash into Dimorphos at 14,000 miles per hour, and measure how much the impact changed its orbital period around Didymos. DART carried no scientific instruments for studying the asteroids. It was purely a kinetic impactor, essentially a guided missile designed to test whether humanity could deflect a potentially hazardous asteroid. The spacecraft used ion propulsion and autonomous navigation systems to home in on its target with pinpoint accuracy. Mission controllers at Johns Hopkins Applied Physics Laboratory in Maryland could only watch as DART approached its target. Since the 7 million mile distance meant radio signals took several minutes to travel between Earth and the spacecraft. The final approach relied entirely on DART's onboard camera and navigation system to guide it to impact. Perfect impact. At exactly 7:14 p.m. Eastern Daylight Time on September 26, 2022, DART achieved what many considered impossible: a direct hit on a target the size of a football stadium from millions of miles away. The impact occurred with the force of several tons of TNT, creating a spectacular explosion visible to ground-based telescopes worldwide. Andy Rivkin, the mission's investigation team lead at Johns Hopkins Applied Physics Laboratory, confirmed that DART struck within 17 meters of Dimorphos's center, a bullseye by any measure. The impact was captured by DART's own camera in its final moments, showing the rocky, boulder-strewn surface of Dimorphos rushing toward the spacecraft at incredible speed. Simultaneously, LISIACube, a small Italian-built observer spacecraft, photographed the collision from a safe distance, capturing images of the impact plume and debris cloud. Telescopes on Earth, including the Hubble Space Telescope and James Webb Space Telescope, immediately began tracking the aftermath. The impact created a massive debris tail stretching thousands of miles behind Dimorphos, visible as a bright streak against the darkness of space. Initial observations confirmed the mission was an immediate success, but the real surprises were just beginning to unfold. The shocking results. The impact results exceeded all expectations in ways that left scientists scrambling to understand what had happened. Pre-mission calculations predicted DART would shorten Dimorphos's orbital period around Didymos by approximately 10 minutes. Instead, measurements revealed the orbital period had decreased by 32 minutes, more than 3 times the predicted change. Tom Statler, NASA's DART program scientist, called the results remarkable and far beyond their most optimistic projections. The massive orbital shift suggested Dimorphos was much less dense than anticipated, behaving more like a loose pile of rubble than a solid rock. Andy Cheng, the DART investigation team co-lead, explained that the enhanced momentum transfer indicated the asteroid was essentially a rubble pile held together primarily by its own weak gravity. The impact had not only displaced material from the collision point but also triggered a cascade effect where ejected debris contributed additional momentum change. This discovery revolutionized our understanding of small asteroids. Many are apparently fragile, loosely bound collections of rocks and dust rather than solid objects. The finding has profound implications for future asteroid deflection missions, suggesting smaller impactors might be far more effective than previously thought. The debris mystery. Months after impact, Dimorphos continued surprising scientists with its ongoing transformation. Hubble Space Telescope observations revealed that the asteroid was still ejecting material long after the collision, creating multiple debris tails that evolved and changed direction over time. John Yang Lee from the Planetary Science Institute led analysis showing Dimorphos had developed at least 3 distinct debris tails spreading in different directions. The continued material ejection suggested the impact had fundamentally destabilized the asteroid's structure, causing ongoing landslides and surface collapse events. Christina Thomas from Northern Arizona University reported that Dimorphos was losing mass at a rate much higher than expected, with debris continuing to stream away from the impact site months later. Some debris particles were moving fast enough to escape Dimorphos's weak gravitational field permanently, while others were falling back to the surface in slow motion. The European Space Agency's upcoming Hera mission, scheduled to arrive at the Didymos system in 2026, will provide detailed analysis of the impact crater and ongoing surface changes. This extended debris emission was completely unprecedented and suggested asteroid impacts could have much longer-lasting effects than anyone realized. Surface secrets revealed. The impact revealed Dimorphos to be far more complex than a simple space rock. High-resolution images from the final moments before impact showed a surface covered in large boulders, some measuring several meters across, scattered across relatively smooth terrain. Olivier Barnouin from Johns Hopkins Applied Physics Laboratory analyzed the surface features and determined that Dimorphos likely formed from debris shed by the larger Didymos asteroid over thousands of years. The boulder distribution pattern suggested the moonlit surface was actively changing, with rocks gradually migrating toward the equatorial region due to Dimorphos's rotation. Patrick Michel, principal investigator for the upcoming Hera mission, noted that the impact site appeared to be in a region of relatively fine material between larger boulders, which may have contributed to the unexpectedly large momentum transfer. Spectroscopic analysis of the debris cloud revealed that Dimorphos has a composition similar to carbonaceous chondrite meteorites, suggesting it contains primitive materials from the early solar system. The asteroid's low density, approximately 1.17 grams per cubic centimeter, confirmed it was indeed a loose agglomeration of rocks and dust, with significant empty space between particles. This porosity explained why the impact was so much more effective than predicted. Asteroid defense revolution. The DART results revolutionized planetary defense strategies and demonstrated that deflecting potentially hazardous asteroids might be easier than previously thought. Lindley Johnson, NASA's planetary defense officer, announced that the mission's success validated kinetic impact as a viable technique for asteroid deflection. The unexpectedly large momentum change meant smaller, less expensive spacecraft could potentially deflect threatening asteroids with sufficient advance warning. Alan Harris from the Space Science Institute calculated that a DART-sized impactor could deflect most potentially hazardous asteroids if deployed years before predicted impact. However, the mission also revealed critical knowledge gaps about asteroid composition and structure that must be addressed for future defense missions. Amy Mainzer, principal investigator for NASA's Near-Earth Object Surveyor mission, emphasized that better characterization of asteroid properties would be essential for selecting appropriate deflection techniques. The DART success led to accelerated development of the NEO Surveyor Space Telescope, designed to discover and characterize potentially hazardous asteroids before they pose threats to Earth. ESA's Hera mission became even more critical, as it will provide detailed post-impact analysis necessary for planning future deflection missions. The success transformed asteroid defense from theoretical possibility to proven capability. The Hera investigation. ESA's Hera spacecraft, which launched in October 2024, represents the second phase of humanity's very first asteroid deflection experiment. Patrick Michel, the mission's principal investigator from Côte d'Azur Observatory, designed Hera to carry out a detailed forensic analysis of DART's impact effects. The spacecraft is set to arrive at the Didymos system in December 2026, and will spend about 6 months mapping both asteroids with honestly, unprecedented precision. Hera is equipped with advanced instruments including a laser altimeter, a thermal infrared spectrometer, and high-resolution cameras that can reveal surface features down to centimeter-scale resolution. The mission will also deploy 2 CubeSats, Juventus and Milani, to study the asteroid's internal structure using low-frequency radar and gravimetric analysis. Ian Carnelli, Hera's project manager, explained that the mission will measure the exact size and shape of DART's impact crater, determine how much mass was ejected, and analyze the ongoing surface changes. Hera will also investigate whether DART created a so-called moonquake that continues to affect Dimorphos' structure. This mission really stands out as an example of unprecedented international cooperation in planetary defense, combining European spacecraft technology with the analysis of an American impact experiment, all to benefit humanity as a whole. Unexpected discoveries. The DART mission, revealed phenomena that scientists never anticipated and are honestly still struggling to explain. Tony Farnham from the University of Maryland discovered that Dimorphos developed multiple debris tails that actually changed direction over time, suggesting there are some pretty complex dynamics happening within the Didymos system. Some of the debris seemed to be following orbital mechanics around Didymos, while other material was just escaping the system entirely. Fernando Moreno from the Institute of Astrophysics of Andalusia used computer modeling to show that solar radiation pressure was sculpting those debris tails into these really intricate patterns that could even be seen from Earth. The impact also appeared to have altered Dimorphos' rotation rate, though of course precise measurements will have to wait until Hera arrives. Masatoshi Hirabayashi from Auburn University proposed that the impact might have triggered landslides and surface restructuring that are still ongoing months after the collision. Spectroscopic analysis of the debris revealed water ice signatures, which was a big surprise given Dimorphos' location in the inner solar system. Simone Marchi from the Southwest Research Institute suggested the impact might have exposed subsurface materials that had been protected from solar heating until now. All these discoveries really showed that even a so-called simple kinetic impact can trigger cascading effects that fundamentally alter an asteroid's properties, behavior, and appearance for quite some time. Global implications. The DART mission's success, honestly, triggered worldwide investment in planetary defense capabilities and led to new international cooperation agreements. NASA announced plans for multiple follow-up missions, including advanced impactor designs and gravity tractor concepts for more precise control over asteroid trajectories. Meanwhile, China's National Space Administration revealed plans for their own asteroid deflection tests, and Japan's JAXA proposed missions that would combine sample return capabilities with deflection experiments. The United Nations Office for Outer Space Affairs began developing international protocols for planetary defense coordination, recognizing that asteroid threats really do affect all nations equally. ESA expanded their space situational awareness program to include enhanced asteroid tracking capabilities. The mission's success also sparked private sector interest, with companies like SpaceX and Blue Origin proposing commercial asteroid deflection services. Brent Barbee from NASA. Goddard Space Flight Center is leading efforts to develop standardized mission planning tools that any space agency could use for asteroid deflection. DART's results were incorporated into updated planetary defense protocols, which are now shared through the International Asteroid Warning Network. Most significantly, the mission proved that humanity actually possesses the technology to protect Earth from asteroid threats, transforming planetary defense from science fiction into an operational capability that keeps evolving through international scientific collaboration. Future of planetary defense. The DART mission, honestly, marked the beginning of humanity's active role in solar system dynamics, with some pretty far-reaching implications for space exploration and planetary protection. Amy Mainzer's NEO Surveyor mission, launching in 2028, will use lessons from DART to better characterize potentially hazardous asteroids before deciding on deflection strategies. NASA is already developing advanced kinetic impactors with enhanced targeting systems and multiple impact capabilities for dealing with larger asteroids. ESA, on the other hand, plans follow-up missions to test gravity tractor techniques that could offer more precise trajectory control for sensitive deflection scenarios. The success of DART validated kinetic impact as humanity's first line of defense against asteroid threats, but it also made it clear that we need a better understanding of asteroid internal structure and composition. Organizers of the Planetary Defense Conference now use DART results as baseline data for impact deflection scenarios. The mission also established templates for international cooperation in planetary defense that go beyond political boundaries. Johns Hopkins Applied Physics Laboratory continues to analyze DART data to refine impact models and improve future mission designs. Most importantly, DART proved that with enough advance warning and international cooperation, humanity really can actively protect Earth from cosmic threats. The mission transformed us from passive observers of celestial mechanics to active participants capable of altering the trajectories of worlds. NASA hit an asteroid and wow, unleashed discoveries that are still reshaping our understanding of planetary defense. DART's impact on Dimorphos went way beyond expectations, proving that humanity can successfully deflect potentially hazardous asteroids, while revealing just how complex and dynamic these cosmic visitors really are. The mission showed that even small impacts can have massive results, transforming planetary defense from a theoretical possibility to a proven capability. With Hera arriving in 2026 to complete the investigation, we're stepping into a new era where humanity actually protects Earth from space threats. So, be sure to subscribe to Stellar Tech for more groundbreaking space discoveries that are defining our cosmic future.